do this so I don't forget. So 2,880, not a perfect square. What's the biggest perfect square that goes into it? So start with the big numbers, and you literally do the biggest number on your list is 625. If that gives you a decimal, you try 576. If that gives you a decimal, you try 529. And you keep going until you find a number that divides it without a decimal. Anyone find it yet? $18 is not on the x squared list, if that's what I heard. So you only are dividing by perfect squares. So divide by 625. Then 576. What would you try after 576? 529. And you literally just go backwards. Anyone? What perfect square goes into 2,880? Did anyone start with big numbers? Not the little numbers? Doesn't 576 go into it?
44 does.
What?
5.
You guys, 576. Did I not say like 5 times start with the big numbers and go backwards? So does 576 divide this?
Yes.
How many times? 5. So start with big numbers and go backwards. Like 80, 16, all those other ones work, but they're not the biggest. So when you guys are looking for a number, start with the big numbers and go backwards. Because 576, what's the square root of 576? What is still stuck on the inside? 5. If you would have taken out a different number, you could have broken that down more. So always start with the big numbers. Do we all understand where that 576 came from? Literally just divide without a decimal. So you guys have been doing square roots since like December. What it's going to expand to this unit is now, instead of just looking at powers of 2, we can look at other sorts of powers. So 8 to the 3rd. So on your yellow sheet, go to 8, go over to the 3rd column. What's 8 to the 3rd? 512. In this unit, there are different types of roots. So a square root means you're going to see what number times itself 2 times equals whatever. This makes it a 3rd root. So that 3 is called the index. If there's a little number in the nook, the difference is now instead of thinking what number times itself 2 times, it's what number times itself 3 times. So when you look at the list of x to the 3rd, is 729 on it? Yes. Go over to the left. What is the 3rd root of 729? 9. So the idea of a root means you're going backwards through the power. 729 is a 3rd power. So then a 3rd root just means what number times itself. Next one, again, 3rd root of 16. So we're trying to figure out what number times itself 3 times. Is 16 on the list of x to the 3rd?
No.
No. What number in the list of x to the 3rd divides 16? 8. So when we break down a radical, the idea of breaking down a radical, it's always the same process. It's just what does it turn into? Here, the square root of 100 made it a 10. So when we take the 3rd root of 8, what's the 3rd root of 8?
2.
And then that other 2 is still stuck on the inside. So breaking it down a radical, same process every time. It's just what type of power breaks it down. If there's a 3 in that little nook, that's the index. That means we're looking at 3rd roots. So we have to look at the x to the 3rd power. 3rd root of 500. And your x to the 3rd, is 500 on there? No. What number on that list divides 500?
125.
How many times?
4.
Should be 4, I think. So, the 3rd root of 125. What number times itself 3 times is 125? 5. Literally, you just find your 125, go all the way over to the left. That's what it's going to turn into. So the 5 is a big number. It comes out. That little 3 that's in the nook is just telling us what type of radical it is. What number is still stuck on the inside? 4. So because there's a 3 in the nook, it's a third root. So we have to look at powers of 3. Next one. Now what sort of powers are we looking at? 4. So you can use this sheet to find exponents. So 10 to the 4th, go down to 10, go over to the 4th power. What is 10 to the 4th? 10,000. Because that 4 is in the index, that means we're thinking what number times itself 4 times is that larger number. A 4th root just means when you reduce it, you have to look at the x to the 4 list. So first thing you do is glance down that list. Is 20,736 on there? Yes. What is the 4th root of 20,736? 12. You just go all the way over to the side. So this sheet is your perfect powers. If it's on the list, when you take a root of it, you just find that number, go all the way over to the left. 162. If you go down your x to the 4, and again we're doing the 4s because it's a 4th root, is 162 on that list? No. So you have to find the biggest number on this list that divides 162. 81 times what? 81 we have to be careful with because we're really used to 81. The 4th root of 81. What number times itself 4 times is 81? 3. So the 81, when you're looking at the 4 list, you go all the way over to the side. It turns into a 3. What is still stuck inside our 4th root? The 2. Yeah.
Can I use the bathroom really quickly?
Okay, next one. Is 1,875 a perfect 4th power? No. So you go down this list. What number divides 1,875?
625.
How many times?
4. Now 3.
When that 625 comes out, you find it on the 4th list. Go all the way over to the left. What's the 4th root of 625? What is still stuck inside our 4th root? 3. So reducing radicals, we're going to do a whole bunch of it in this unit. We do it all week. Today's kind of just like the first day of it. This sheet is going to kind of be your best friend when it comes to it. What power do you think this last row is going to deal with? The 5th power. So in your notes, the last page, like there's an extra blank page. Try these 4. Can we not have this out All right, so copy these 4 down. See if you can figure them out. I'll give you like a laugh and a half. Yep, just the bottom row. So same process, except for now you're looking at the 5th powers. Yeah. Yeah. No, I don't even think I've put those in yet. Yeah. And when you click it, it's gonna say complete, but on my side, like I can tell if it's done or not. So very amazing. $224. But do you see how that 5 is in front? It needs to be literally like in the nook, because otherwise it means something different. But yeah, your numbers are good.
It's like perfect.
Alright, 3 to the 5th. 5th root of 59,049. 5th root of 224 is not a perfect 5 power. What perfect 5th goes into it?
32.
Times what? When that 32 comes out, what will it turn into? What is still stuck on the inside? Do you guys notice how the 5 is little and it's in the nook? If that 5 is not little and in the nook, it means something different. So if you wrote it like this, that means like it's a square root of 7. So that 5 needs to be little, it needs to be in the nook. If it's not little and it's not in the nook, it means something different. So make sure you guys are putting little spots for you to actually write it in there. 200,000, is it a perfect 5? No, which one goes into it? Alright, and again, if I put the 5 right here in front, that means it's a square root. Do you see how that looks like a square root? So this 5 needs to be little. It needs to be in the nook. What's the 5th root of 100,000? 10. What's still stuck on the inside? 2. So radicals, handwriting, and how you notate this ends up being pretty big. So make sure you are paying attention to it, where that little number in the nook goes. So, radical rules is what we're covering today. Friday we did exponent rules. Today we are going to do radical rules. If you guys could put everything else away, that'd be cool. And for the radical rules, they are much less specific than exponent rules. Like exponent rules, there's a lot of like different types of rules. Radical rules, there's not that many different types of rules. However, the way that they can present themselves makes it a little bit trickier. So the examples that you guys see here, we are going to do extra examples kind of just based off of how the other class did with the homework. So I'm trying to like help you guys out so you guys don't get as stuck. First of all, what is a radical? A radical, the way I think of a radical is it's undoing a power. So like a square root is undoing a second power. A third root is undoing a third power, and so on. Vocab wise, N is called the index. The index tells you what type of root it is. So like if you have a little 3 in that nook, that means it's a third root, so it undoes a third power. If you have a little 5 in there, that means it's a 5th root, it's undoing a 5th power. B is called the radicand. So whatever is underneath a radical is called a radicand. Kind of just a heads up, if you ever see like the radicand it's just whatever's under the radical. The big thing for us is the index, because our index tells us what type of radical it is. Again, only 3 rules we're going to go through, but the way that they show up in the examples can kind of make it a little bit trickier. You guys have been doing these rules unofficially all year. Main thing about radical rules is in order to use radical rules, the indexes must match. So like a square root does not work with a third root. A 5th root can't work with a square root. Like they have to be the same type of radical. Just like you can't combine an x squared with an x to the third, they have to be the same type of power, the same type of root. Product property, if you have a radical and the stuff inside is multiplying, you can think of it as 2 separate multiplication pieces. And again, you guys have been doing that. When you like break down the square root of 50, it's the square root of 25 and the square root of 2. So multiplication wise, as long as they're the same type of radicals, they just multiply together. Process wise, and this will make more sense once we get into it, just put outsides together and then insides together. And the good and the bad thing about Algebra 2 is it's hard to do everything in isolation. So you guys have used this rule before. Outside radical stuff multiplies together, stuff inside the radicals, they also multiply together. The second rule, the quotient property. If you have a radical of a fraction, does that radical go to the top, the bottom, or both of them? both of them. So you guys have, again, done this before. So if you have a fraction, the radical goes to both. And then before I go to the third one, remember the idea of equality? Equality means the left side and the right side have to be the exact same thing. So you know how we're writing these rules like left goes to the right? They mean the same thing the other way. And that'll just a heads up, like these rules kind of work both ways. The last one, the addition property, is probably the most finicky one. Do you see how these radicals are the exact same? So underline that those two radicals are the exact same. When you guys are adding, first of all, the radicands need to match. And as long as your radicands match, you're really just combining like terms. So even though the addition property, same thing as subtraction, I just put them together, you're really just combining like terms. And if you think of it in terms of like, if I have 4x plus 5x, what's 4x plus 5x? 9x. So because these are both x's, you see how the front numbers just kind of do the math? As long as your radicands are the exact same, your front numbers are just going to do the math. And once you see these in a couple examples, not a big deal, but for adding and subtracting, your radicands, your radicals, they have to be identical. As long as those are identical, the front numbers change, the radical just kind of stays the same. So we only have 3 rules, but they can present in so many different ways, and kind of the same thing for exponent rules. If you solve the problems in a different way, that's fine. I'm going to show you guys how to solve them most consistently in the same order, with hopefully the least amount of like weird stuff that can pop up. First example, we're multiplying. Do you notice how they're both third roots? So third roots, you can put them together. So what is 12 times 18? Because your insides multiply together. 116.
16.
And then just like at the end of every problem, you reduce your radicals. So when we multiply them together, the insides multiply together to give us the third root is 216. And then just reduce your radical. Since it's a third root, you look at your x to the third list. Is 216 on there? Go all the way over. What's the third root of 216? 6. So our final answer is just 6. So always reduce your radicals at the end, but I would suggest doing the operation first. Okay, the next one, number 2. What sort of radicals do we have? A fourth root. Do you see how they're both fourth roots? So since they're both fourth roots, they can go together. Here's the issue with it. This 5 on the bottom. Can we take the fourth root of 5? Is 5 on this list? No. Do any of these numbers divide 5? No. So there's an easier way to think about this one. Not that it's the only way, it's just the easier way. If you have a radical on top and bottom, that's the same thing as saying I can write it this way. So like if you have a radical on both top and bottom, that's the same thing as saying you have one radical of the fraction. So those two things mean the exact same thing. The perk of writing it this way is we can actually do what's 80 divided by 5? 16. So we still haven't taken the radical yet, but we've reduced that fraction. And now, what's the fourth root of 16? 2. So it takes it from a problem where you can't take the fourth root of 5. The fourth root of 80 is kind of weird, you have to break it down. But if you have a fraction with a radical on top and bottom, you can just reduce your fraction first and then take the radical of it. So do you see how we just like rewrote it the other way and then it's a lot simpler? All right, number 3, what operation are we doing? Multiplying. They're both third roots. So since they are both third roots, the insides multiply together. So what's 4 times 128? 512? reduce. Look at what list. So what list do we have to look at? The 3 list, is 512 on there? What does it turn into? So it's not always going to be the case where they turn into nice numbers, but the idea of like you just reduce your radical. Adding and subtracting. Do you see how these are both 4th roots of 10? For that 10, since they're the exact same, this one has a 7 in front. Our first radical, what number is technically always there? A 1. Don't overthink this. If I have 1 4th root of 10 plus 7 4th roots of 10, how many total do I have? 8 4th roots of 10. So as long as your radicals are the exact same, your front numbers actually combine. You're just combining like terms. The radical part does not change. Can we take the 4th root of 10? No. Do any of the 4th numbers go into 10? No. So we're just done right here. So as long as your radicals are the same, your front numbers do the adding and subtracting. On number 5, are our radicals the same? No. So when we're subtracting, this 54 and this 2 cannot be combined together. So what we have to do is first see, can we reduce our radicals to get them to match? 54 is the bigger number. So like, let's see, can we reduce our 54? In the 3rd list, is 54 a perfect 3rd power? No. What number goes into 54? 27 times what? So looking at just the 54, we can break it down into 27 times 2. When that 27 comes out, what's the 3rd root of 27? 3. 3rd root of 2 is left over. So our first radical we can reduce. The second radical, does anything come out of 2? No, so I'm just going to copy that down. Make sure you still have that little 3 in the nook. If you don't have a number in front of your radical, you can always just put a 1 there. Once your radicals are the exact same, you're just combining like terms. So how many of these 3rd roots of 2 are we going to have? 2, because it's just 3 minus 1. The radical portion does not change, only the front number does. So you make the radicals be the same. Once they're the same, you're just looking at the front numbers. Okay, next one, as is. Can we combine those together? No, 5 and 40 don't match. So when you're adding and subtracting, this is when it gets specific and they have to be identical. 5, can anything break down 5? No, so that one is just stuck. The 40, what breaks down the 40 when you're looking at the 3 list? 8 times 5. When that 8 comes out, what will it turn into? And then you still have the 3rd root of 5. Make sure that 3 is little and in the nook. This other 3rd root of 5 doesn't have a number in front, so what number can we always put there? A 1. Once your radicals are the exact same, just change your front numbers. So what's our new front number? And then we still have 3rd root of 5. So radical rules, there's not as many of them, but it's a little bit more like, how do we set this up to make this work? You have a blank page afterwards. Now we're going to just do some random ones based off of where the confusion was in the homework. And I kind of purposely made these notes shorter today because there's so many different ways to solve these that I don't want to like make people feel like they have to do them one way. What operation does it mean when we have parentheses touching? Foil. It multiplies, so we have to FOIL it out. You guys have been foiling stuff like this out, and this is where the whole like inside-outside thing comes into play. When we do our first FOIL, do you see how the 6's are both under the square root? So inside stuff does multiply together. When you do the square root of 6 times 3, can a number outside a radical multiply with one inside the radical? No. So the 3 stays outside, the 6 stays inside. When you do the negative 2 times root 6, can the 2 multiply with the 6? No, the 2 stays outside, the 6 stays inside. When you do the 2 times the 3, can those multiply together? Yep, they're both outside the radical, so they multiply together. I don't know why I made a little parenthesis there. So, inside radicals multiply together, outside radicals multiply together. What is the square root of 36 equivalent to? Those are both square roots of 6. What's 3 root 6 minus 2 root 6? 1 root 6, or just the square root of 6. What else can be combined together here?
6.
Yep, those cancel, so final answer, 1 root 6, or just root 6. You don't need to put 1s in front. So, FOILing is really just a way of multiplying. Inside the radical stuff goes together, outside the radical stuff goes together. Questions on that one? Okay, one more. Hopefully this works out. Okay, when you have a radical that is dividing, instead of thinking of it as 2 separate radicals, you can think of it as just one big radical with the division on the inside. So those 2 things are equivalent. Why is it easier to rewrite it as just one big radical? Yeah, then you can simplify it. So what is 729 divided by 3? So if you have a fraction, you can simplify it first. What's the 5th root of 243? What is it? 3. So as you guys are going through these, if you get stuck or you have any questions, let me help you. Tomorrow